Excellent. Okay, thank you very much. Thanks for hosting me. So I'm Robin Priest. I'm a reader, which is a weird UK title, which essentially means associate professor in future power systems from Manchester. Um, yeah, so the provocative part of the title is, do wind farms make blackouts more likely? The kind of technical bit is basically using dynamic models of cascading failures. So it's a presentation about doing some cascading failure analysis and then incorporating dynamics into that, because typically the dynamics of cascades are not modeled, and then using that to work out how that changes the results and see what happens when we shove a load of wind farms in the system as well. So for those who've never been, I come from this building. This is our new building. This is our new engineering campus. So we built this about 2 or 3 years ago. Well, it took about 5 years to build, but we moved in about 2 years ago. And this holds all of engineering, essentially, at the University of Manchester. It used to be an entirely separate university called UMIST, University of Manchester Institute of Science and Technology. There's quite a few old ex-UMIST graduates dotted all around the world. We've moved away from that campus. That campus got really old and quite hard to maintain. And we've moved into this shiny new building. And it's quite nice for me because I used to be in a part of the other building where it was only research students. And so I could go in to work and I would only ever see maybe 5 people for the whole day. That would be it. I'd never see anybody else. Whereas now in this building, the bottom 3 floors are full of undergrads all the time. So it's quite nice. It feels like being more part of the uni. We're the largest single site university in the UK, Manchester, about 40,000 people, lots of undergrads, lots of postgrads, and a fair few researchers as well. In terms of EEE, so electrical electronic engineering, which is my department, this number actually might be a little bit out of date. This 700 is probably maybe more like 800 or 900 now. We've had a real drive to increase the number of undergraduate students because we're short on money and there's a whole financial question around the sustainability of higher education in the UK. So we're trying to increase our numbers. We've got about 350 taught postgraduates doing master's courses and maybe 250, 300 doing PhDs, and about 85 academics across electrical electronic engineering, which makes us pretty much the largest EEE department in the UK. This is me standing in front of an impulse generator, pretending I do actual practical stuff, but just posing for a photo. So I've been at the university for about 19 years. I went there as an undergrad. So I started my BEng in 2005. I moved to Manchester. I then spent some time working at a UK DNO, distribution network operator, decided I didn't want to do that long term. Came back and did a PhD. I then spent some time during my PhD working at National Grid. They sponsored me, so I spent a lot of my time with them. Then I started as an RA. This isn't meant to be like a downward trajectory to my career. I should probably reorient it. But I then started as an academic about 10 years ago. And so I've been an academic at the university since then. For the technical thing, I'm going to start from the perspective that we're all going to accept that we need some cascading modeling. I'm not necessarily, so I think that's true. In terms of cascades, there are definitely situations where you see cascades happen. They're quite rare, but when they happen, they're pretty catastrophic. So that's kind of the argument here. They're not a thing that happens a lot. They're a thing that happens very, very rarely. But when it happens, it causes big, big issues in the system. In the UK, about, I don't know, 2019, we had some kind of frequency-related problems that led to millions of people being disconnected. In Italy, they seem to keep having it. It's a bad part of Europe. Italy's a lovely part of Europe. It's a bad part electrically because they seem to always bear the brunt of European disconnection things. They always get separated from the rest of the system. And so we have these cascades that happen. And so it's a useful thing to be able to quantify how is that cascade affecting the system? What's the risk associated with it? These are very unlikely rare events, but obviously as we increasingly electrify our systems and we're increasingly reliant on that electricity, we definitely need our systems to be like resilient. And so that's why there's a big interest in keeping our systems operational as much as possible. So I come from a Ah, you've been fiddling.
I'm sorry.
It's all right. I come from a dynamics perspective. And so my interest is like, okay, I'm going to put some dynamics into the cascade and see what impact that has. Should I bother doing this? Is essentially the question we were trying to ask, trying to answer. Like, should I bother going to all the effort of building a dynamic model of a cascade? Is that going to give me a fundamentally different understanding of the risk associated with the system? Because if it doesn't, then this is a waste of time. Okay, so it's kind of like, what's the point in doing this modeling? Let's see if it helps. And so then there's the question of, okay, well, which dynamics? Because dynamics is just anything that changes with time. And so there's an awful lot of opportunities and options that you have here. So we can start with the kind of traditional frequency kind of stuff, which can span from essentially instantaneous response after a disturbance in the inertia range through primary control into kind of secondary AGC control. So how we kind of reschedule our generators and bring our frequency back. We've then got voltage regulation problems. So stuff with voltage, how that's affected by demand, how power rebalancing within our system is going to affect that stuff. And then we've also got down here, it's like, what are the protective devices that are operating on these different ranges as well? So if there's a faulty element, how long does it take to remove that from the system? If we've got under frequency load shedding or under voltage load shedding, how long does that take to operate? We've got things like branch overload protection. So if a line gets overloaded, at some point we need to trip it out because it's going to melt. We've got overexcitation, underexcitation limits on our generators. We can redispatch those generators. And again, we can choose to redispatch our demand if we have control over it as well. So there's all of these potential options. And I'll tell you now, doing all of it is too much. So we couldn't do all of it. We had to make some choices, especially as a kind of first pass. And so I'll come back to which ones we chose in a bit. So for us, we were looking at, okay, the other option is static models. So I could, and here when I say static, I'm going to start with just an assessment of DC power flow. So these are the super quick ways of assessing the power flow in your system. So a DC model. So great, reliably convert. I say converge, it's not really converging, is it? It's just like a direct solution. Very computationally fast. You can easily capture things like line overloads. So it's great. DC power flow will tell you the line loading. Like obviously it's inaccurate to some extent, but gives you a good estimation of line overloading. I can redispatch generators. I can deal with those kinds of things very easily. And it gives acceptable consistency with historical data. So there's been a lot of work looking at using DC models for cascading failures and looking at how does that match up with historical work. And it's pretty good. So maybe we don't need to worry about adding in all these dynamics. Some of the problems, obviously this neglects voltage deviations, reactive power flows, things associated with that. You can then fix that using AC power flow. So you can bring in some AC power flow stuff. But obviously the big one for me, neglected all the dynamics associated with it. And I guess the reason I'm concerned with dynamics, if I look at, I mentioned there was that the under frequency event in the UK, 2019. Now, that event, parts of the country tripped off. So some parts of the country experienced under frequency load shedding. Other parts of the country did not. So what that means is that in some parts of the country, the frequency dropped too low. And in other parts of the country, the frequency never went low enough to trigger that. They all have the same settings. So that means we've got variation, regional variation in our frequency within that system. If there was just one singular frequency, then everybody would have experienced that across the country. They'd have all experienced that under frequency load shedding. So I know there's regional variations in frequency. It's that kind of dynamics that I want to be able to capture. I want to see how does having an under frequency event in this part of the network lead to these people being tripped off, and that then having a stabilizing effect for another part of the system as well. I want to tie all of that together. And I'm going to argue as well, dynamics increasingly important due to these things. So if we're adding a load of wind farms or solar or anything which doesn't have a big spinning mass of metal at its core within its generator, then I'm then experiencing issues with kind of lower inertia systems. So I've got less synchronous energy within the system, which means when I have a disturbance, the rate of change of frequency is going to be much higher. And therefore, this is kind of my motivating factor. This brings us back to the initial question. What happens if I put more of these into a system? Is it going to increase the risk or not? So in terms of these dynamics, we had to make a choice, and we chose these ones. So we sacked off everything to do with voltages. It's too hard. Voltage, the amount of voltage controlling devices that you have within your system is extremely large. And it's a very, very complex thing. It's, I mean, super interesting to study. It's definitely not like we're saying you don't need to worry about this. What we're saying is we didn't worry about this now. We're going to worry about it in the future. We're going to start with the frequency question. So we're going to look at the inertial response, the primary control. We're not too worried about the AGC because it's essentially too slow for us to worry about during these kind of fast cascading events. So we're going to model under frequency load shedding, but we're not going to model any of the under voltage load shedding. And so within our model, we essentially kind of voltage lock it, and we just make it incredibly robust from a voltage perspective, so that we can see all the frequency changes there. In terms of test systems, we used the Texas A&M ones. I don't know, you might be aware of these, but they build synthetic models. So these aren't the actual models of Illinois or Texas. They are equivalent models that could exist given the load distribution and generation availability, etc. So they build these, and what's really nice about these is that they're just like publicly available. You can get them, and you can get them as dynamic models. So we need to build a dynamic simulator that can then take these and work with them. And once you get to 2,000 buses as a kind of dynamic system, this is pretty large for dynamic studies. This one takes a long time to run, particularly when we stack in all of these various devices and stuff. So our cascading failure simulator, we need an engine for it. So we need something that's actually going to churn through and do all these simulations. And we're using DigSilent. So DigSilent is just a power system dynamic software simulation package. We use that because we've got a lot of experience using it in Manchester. And we have a lot of experience using it in Manchester because National Grid use it in the UK. They use it as their like default power system simulator. So we've built up expertise and skills using it to make sure that we can then translate our work into industry and have some industrial impact coming out of it. We need to model synchronous generators. So as I say, we're ignoring the voltage stuff. So we're just modeling these as classical second order models. So that means it's got a swing equation. It's got a couple of dynamic states associated with the mechanical system. But from the voltage perspective, it's just a constant voltage output. So we've got no voltage control associated with those, but we do have the primary control. And apparently we've got secondary control. For demand, demand doesn't matter too much. We are actually modeling it with a zip model, but like I said, we're not worried about the voltages in the system. So the actual voltage dependence within this doesn't really matter. This could just be a constant PQ load. It would be the same result. We have some frequency dependence on the demand, but it's quite small. It doesn't have a big effect on the result. And then in terms of protection, whoops, where did that go? In terms of protection, we need to have over/under frequency relays on our synchronous generators. So they'll trip out if the frequency gets too high, they'll trip out if the frequency gets too low. They have an out of step relay. So essentially if they over rotate and they lose synchronism, they'll trip off. We have thermal protection on the lines. So if the line gets too hot for too long, we trip it off. Some countries don't actually do that. They will manually do that. They will use it thermal alarm systems, but they will rely on a manual tripping. We obviously need to automate this within the simulation. So we automate a thermal protection on that. And we have under frequency load shedding as well. So we have the kind of standard tiered under frequency load shedding. So as the frequency drops, you disconnect your load in slices. And I think for this, we used whatever the US setup is. I can't remember off the top of my head, but we use the same kind of under frequency limits. So that's our dynamic model. And then we're going to compare this to a static. We're going to use the DC OPF. So the difference here is that that runs a power flow. And then if it sees that a line is overloaded, it collects up all the overloaded lines, just trips them all off. It will then redispatch the generators according to the new topology. It allows some variation in some of those generation and loads. It allows them to move a little bit, essentially to emulate the behavior that you would get from some kind of frequency response. And it includes over frequency generation tripping. So essentially, if I have an island where there's too much generation, it will then start disconnecting the generators from starting from like the smallest one in order to try and find a kind of a static operating point that converges. So we've got some kind of emulation of some of those dynamic processes within this, but it's obviously not running the actual dynamics itself. So those are our two different models. And then to trigger any kind of outage, we're using n-2 contingencies. So these systems are safe for n-1. They're fine, like secure for an n-1 situation. So we need to hit them with an n-2, something more significant in order to cause a problem large enough to start a cascade. And most n-2s don't. Most n-2s are fine. It's only some of them that actually cause problems. That's actually a really interesting question is, how do you find out which of the initial contingencies you need to cause an to cause a cascade in your system? It's not a trivial question to know where the kind of combinations of multiple outages will be that lead to a big cascade in the system. So we need to figure that out as well. So main result, you get different results when you use dynamic cascades. Okay, so we actually see a difference. So here we're going to plot essentially a probability, a cumulative probability plot of unserved demand versus the actual amount. So if we see the static one, what this means is that there is a very low probability essentially of losing very small amounts of demand. Sorry, a high probability of losing a low, and then as you go down the curve, we then see very low probabilities of essentially total blackout in the system. So this is the classic way that we plot the results for cascading failures, and this kind of curve is what you would expect. Okay, so this is what you get when you look at this. If we do a dynamic plot of this, like a dynamic simulation with the same system, but with our extra dynamics in it, we get a slightly different result. So we have a higher probability of small trips. So we've got a higher probability of seeing small blackouts, like local blackouts, little areas where we've just lost a tiny little bit due to some under frequency load shedding. But we've got a lower probability of larger blackouts. So you can kind of summarize it as like these kind of small trips help save the whole system. And so we're seeing this kind of difference in behavior, and this kind of difference maps through into other aspects. So here, this is a kind of customer-focused metric. So how much power is lost, how many customers are disconnected. This is more of an asset-focused one. So how many of my lines are lost? So we're looking at the percentage of lines in the system. How many of those are disconnected for different contingencies? And again, you see the same kind of curve. And this is getting up to whatever. So up here, we're losing just whatever these numbers would be. I don't know, 40% of all the lines in our system are being lost. If we do it with a dynamic model, we don't get anywhere close to that level of kind of total system blackout where so many lines are being disconnected. Again, a higher probability of a small number of trips, but a lower probability of total widespread blackout. So we see this kind of result, and this is all on the 200 bus system. If we then swap to the 2000 bus system, the actual shapes are kind of the same. It's just like moved, right? So it's slightly different place on the plot, but the underlying relationship is the same. So we still see the same thing. So a much lower probability of seeing huge numbers of lines disconnected. So we're seeing slightly different kind of behaviors in our cascades. And you can see here, just what you can see, we're at this stage where about 10% are causing any kind of blackout. So 90% of my simulations lead to no disconnections whatsoever after the initial outage. So actually 90% of my simulations are wasted. In terms of producing this result, they don't do anything. So that's why I want to try and find a way to find those initial contingencies that lead to these cases, as opposed to the 90% that lead to something else. Yeah, he had a question.
Right. I guess we'll talk about that. I was wondering, how did you simulate the initial, events that is causing the cascading failure?
Yeah, so it's an n-2, and it's a random selection, so purely random. I don't know how many. I will get to it slightly in terms of, do we think these results have converged or not? And for the 200 bus system, yes, we think the results have converged. And for the 2000, not quite. I think this is about 1,000 or 2,000 n-2s. 1,000 n-2s is enough for this to be confident that the shape of this plot doesn't change. For this one, we're not quite there yet, but we essentially ran out of time. So yeah, so we're doing random. You could do other methods. So there's certainly techniques out there that once you find one contingency that causes a problem, you might want to like try and resample and use that information and go, okay, well, what if I keep this line and try some other lines, or keep the other line? And like there are more sophisticated search methods you could use to try and find more of that. The danger is that you don't then necessarily know how much you've shifted your search space. So at least if you use a purely random approach, we know that this is a true reflection of the probability. So it's the probability conditional on any n-2 has happened. But if you start directing your search space, it's then harder for you to kind of map that back to a true probability at the end. So that's why it's a fun problem. So some of the reasons for the difference. So model granularity, we are, if we look at, particularly with respect to this, so outages are lumped. So in the static model, let's say in one iteration, 3 of my lines get overloaded. I then disconnect all 3 lines, and then I will then do the next iteration. In the dynamic model, there's essentially a time dependence on when it trips, depending on how overloaded it is. And so then if it's very overloaded, it will trip faster than if it's just mildly overloaded. We'll let that run for a much longer time. And so that means that your tripping events for lines are happening at like discrete individual points in time. You won't get 3 lines tripped at once. And so what that means is you might find that one of those line trips then has a nice stabilizing effect on the system, or it might create an island and then those 2 islands are fine. Whereas if you trip all the things out all at once, you might have other issues in the system. So this kind of granularity that you get, this with respect to time, instead of lumping everything together, that's causing some of the difference. And also we see an awful lot of under frequency load shedding. So we can't really represent that within the dynamic model, particularly. We can represent a little bit of load shifting and allowing a load to shift to kind of like redispatch, but it doesn't necessarily represent the behavior very well. And so this under frequency load shedding is really causing quite a bit of the difference. The challenges, so data availability. So being able to model this stuff is really hard. I would say I would never advocate that what we're trying to do here is represent a single dynamic cascade within the system. We are not trying to say that if you have if you gave me a system and I did an n-2, that this is precisely how the cascade would happen. There's too many things that we're ignoring, right? We're ignoring all the voltage stuff. We're not looking at hidden failures in protection mechanisms. We're not looking at human interactions and choices they're making. We're not trying to replicate a precise event. We're trying to build a kind of representative case of what would happen if 1,000 of these things happened in your system. So precise event sequencing is like essentially impossible, I would probably argue. Very challenging. This is why whenever there's a blackout, it takes like a team of 20 engineers, 6 months to then write a report on what actually happened with that. Like it's a huge amount of work to go back in and find out what's happening in the system. So what it is useful is this kind of aggregated risk quantification. So you're trying to find the probabilities. Trying to find the probabilities of risks within the system, and then see how those are affected. Are we all good?
Any question from the audience? All right.
Okay, no problem. Yeah, and then we can use that to then compare statistical things. So it allows us to make some kind of choices to make interventions in the system and then see what effect that has. Computational burden, this is the major challenge. So in order to do this, I'm going to just introduce a couple of quantification metrics. So if we have some probability, we have some expected value of that probability. So we have an expectation, just the average value within this distribution. But we're also going to look at things to do with the tail. So when we're looking at blackouts, we quite often care about the worst case. So here I'm going to use, say, the worst 5%. And then what we can do is we can call this the value at risk. So the value at risk for 0.95 will essentially be the value on this axis. So this might have been the amount of demand lost or the number of lines lost. So this will tell me, say, the number of megawatts that will be disconnected for 95 well, for the worst 5%. So the worst 5% of cases will see a loss at least equal to whatever that number of megawatts is. And then there's another value, which is the conditional value at risk, which is just the average value within the tail, the expectation within this 5%. And so we care about these results as well as the expectation. So if we just look at the expectation, that tells us a good representation of the average, but we might be missing information about the tail. The reason I bring those up is because if we're looking at computational burden, we have this issue of how many contingencies should we use. So this is looking at running this over and over and over again and seeing how does our expectation converge over time. So each one of these lines is another run of a random set of 1,000 n-1s. And if we do that, we can see that we're pretty happy that with 1,000, we've pretty much converged on the actual expectation. This is the plot for the expectation. We do this for the C-bar as well. With C-bar, it takes a little longer to converge because you're converging on a tail, right, as opposed to converging on the average value. But by the time we get to 1,000, we're quite happy. The problem we have is that with the 2,000 bus network, we're not converged yet. So I'm showing you these results, and these results are one of these lines. And actually, if you look at 1,000, there's a pretty big range of what that expectation could be. So by the time we've run 1,000 simulations of n-2s on the 2,000 bus network, really, I have, say, confidence that my expectation is somewhere between about 1,200 and 2,400 or something like that. So it's nowhere near converged to a final answer. And if we look at the C-bar values, that's going to be even worse. So the amount of burden that we have, the amount that we need to run in order to get this to a reasonable solution, that's a real challenge. Things we can do to help with that, we can do things like increasing step size. So at the moment, you take a dynamic simulator, and by default, you're probably running at about 10 milliseconds. Like that's a kind of typical thing that we do for most power system dynamics. You can obviously push this up. You can't push it too far because at some point you're pushing it to a stage where it's not fast enough to see the devices that you're tripping. So if you've got a fast rate of change in frequency, you can't go much faster than this, than about 0.3 seconds, because your rate of change of you might have crossed over a couple of thresholds for under frequency load shedding within 0.3 seconds. So you need enough resolution in your time step to be able to take an action before the next time step would occur. But if we do this and we look at what the results we get out, so expectation is fine up until about 0.2 and then starts to crumble a little. And then the tail values are actually probably slightly more consistent even than the expectation is. So here we're seeing that the tail is surprisingly consistent as we increase the step size. And so similar for the actual kind of average number of line outages across all the different cases. So if we take all of these different plots, and this is last one simulation time, which you can just about see. So we've got about 20 hours there down to about 12 hours here. So it's not a case that you do a 30 times increase in step size and it's 30 times faster. No, it's about 40% faster, something like that. So you get a benefit, but it's still slow. So this is why when we need to push that to tens of thousands of simulations, it's a bit of a challenge. We tend to stick somewhere in this space just because it's kind of an average of computational burden and accuracy. So all of that, no renewables, right? So that was just the normal system. The actual question was, does putting wind farms in make it worse? So now we need to get to that bit. So if we want to add wind farms in, we have to improve the cascading failure simulator. So we need to add some wind generators. So we're going to add type 3s, so defigs. You can add anything. You could add full converter. It's not really going to change too much in this. We're assuming constant wind speed. So we're not looking at wind variation during the lifetime of the cascade. And we give them really good fault ride-through capability because we're not controlling the voltage. So we don't want them tripping off for under voltage things because we haven't bothered to control the voltage. So we're making sure that they're robust to whatever voltage is happening in the system. The voltage is pretty stable, but there is a chance it will dip a bit. So we want to keep these things connected. We also need to add a little bit more protection. So we need to put protection on for the wind generation. So we've got under voltage ride-through, and then we also have them tripping off for over under frequency as well. And then we have to add in frequency containment as well. So our system now is potentially going lower and lower inertia. And so we need to add fast frequency containment services to make sure that for a normal secured event, like an N-1, that frequency is not going to lead to problems. It can't, because otherwise all we're doing is making our system weaker and then concluding that our system is weaker. And that's not good. So we need to build our model appropriately. We also need to do a little bit more work on the setup because we have the same challenge, which is we don't want to just add a load of wind farms somewhere in the network, lead to that part of the network having a load of extra generation, and then that causing overloads on the lines and us tripping the lines because they're overloaded because we never did any network reinforcement that we should have done. So we need to add some of that steps in as well. So we take our inputs, we've got our data, we've got our wind, we've got our FFR. We're just going to assume for this, FFR is fast frequency response. I'm going to assume that that is just evenly distributed across the whole network. You can do a study where you move it around and see what effect it has. It has a small effect, but for this, it's just evenly spread. We then make sure our system is N-1 secure. So yeah, N-1 secure. So we run an N-1 security constrained OPF to make sure that our system can cope with any N-1 on the system without being overloaded. If it fails that, we then do some basic transmission expansion planning. We are not transmission expansion planners, so we basically just look at which lines get overloaded. We then assess them based on how long they are, and we upgrade whichever one would be the cheapest one to upgrade, so typically the shortest. So we come up with the cheapest possible solution to get rid of our overload problem and to make our system N-1 secure again. So it's like, it is not a perfect optimized way to do it, but it is a broadly representative way that leaves us with a system which is N-1 secure, which is what we want. We then size the frequency containment service. So then we look at it and we go, okay, what's the largest infeed in the system? I'm going to disconnect that. I'm going to see how the frequency is going to drop. I'm going to add enough frequency containment to make sure that that frequency comes back up to where it needs to be. After that, we run the cascade and then we do the actual outputs. So these bits, the same as what I was saying before. We're going to do this on the 200 bus system because doing it on the 2000, as we've discussed, we're not sure we're converging on the solution. We're going to look at varying the amount of wind farms, amount of wind penetration in the system from 10 to 60%, and we'll do it with 1,000 N-2s. It's enough. So in this case, if we look at the EDNS, so the expected demand not served, so this is the average of that plot. So this is telling us across all of our various plots, this is how does that risk increase with wind penetration. And so we get this kind of gradual increase, and we see the same thing with our bar values and our C bar values. So we're seeing this subtle but definitely noticeable increase in risk associated with increasing renewables. So then the question is, okay, well, what's causing that? What's causing that demand loss? Can we pin that down to something in particular? So we look at all that demand that's lost and we try and break it down. So this is then going to break it down into kind of zero generation. So that means I create an island and there's no generation in that island. So that island has to be tripped. So these are islands which just get formed but have no generation available. We then have islands with inflexible generation. So they have some generation in them, but they can't move enough. They have some variability, but not enough. They're going to hit their limits, min or max, and therefore it's going to become an infeasible solution and they're going to get tripped. And then the biggest chunk is the under frequency load shedding. So what we see mostly causing the demand loss for our cascades is just under frequency load shedding. So as I increase the amount of wind, I'm displacing my synchronous generators. I'm now seeing faster rate of change of frequency. That's causing more local under frequency variations, and that's causing under frequency load shedding. So that's the story that this result gives us. It's like, okay, so pretty confident that the problem now is something to do with inertia. And if I have inertia in my system and that's what's causing the problem. Okay, right. So then we looked, okay, now what about, does it matter where the renewables go? So in this network, this is just like a graph of the network. We split it into 6 zones. So this is a kind of predefined 6 zones based on the network and where the generation is. And then we're going to look at putting the renewables into each of these zones one at a time. because these zones have different characteristics. So we tried to characterize them in different ways. You can just about see. So inertia. So what's this is like the percentage of the total system inertia that they have, just the number of buses. So how big is that region? The average node degree, it's like a graph metric. So how connected is it? So if this is basically tells you the average number of other nodes that each node is connected to. Okay, so it's usually somewhere between like 2 and 3 in most networks anyway. But this one is here. Average line loading. So how overloaded are my lines, or how close to overloaded are my lines? So these numbers are going from like 0 to 60. And then this is G over D. So this is generation over demand. So essentially, is this region a kind of net exporter of energy, or is it a net importer? And so here we're just a little bit over 100. So that means it's just going to be slightly exporting. Okay. And we do this for all those different regions. So these different regions have different properties. So you can see here, this one's probably the highest inertia. This one's like the lowest inertia, or maybe this one. This one's really quite low inertia and quite heavily loaded already. So these lines are already up to over 50%. This one over here, zone 6, very low loading on the lines to start with. They're down about 20% loaded. So there's loads of extra capacity on these lines. So we kind of looked at these different properties and we're like, okay, let's see if this has an effect. And we do the same thing again, where we increase the renewables in each of these zones. We can't increase it as much because we're constraining it just to those zones. So we only go up to about 50% this time. But to start with, this is just showing you the difference in the need for reinforcement. So this is the transmission expansion planning stage. So how many new lines do I need to build? So zone 6, if we go back, remember zone 6, very low loading on its average line loading. I can put up to 50% renewables in there and I never have to build another line. So I never have to build any new lines to keep this one n-1 secure. These other zones have slightly different properties. So zone 1, by the time I do that last bit, I need to build some extra lines. Zone 4, I need to build more lines. But by the time I've got to 38, I've kind of plateaued. So this is the relationship of, this is just showing how many extra lines do I need to build. And you see here, zone 5, this was the one I think that had the highest line loading. You can see I have to build a lot of extra lines to be able to get the power around that part of the network. And so obviously these zones have very different properties. So then it's like, okay, we probably expect some difference in the results. And we get quite a lot of difference in the results. And what you see is that if you put the renewables somewhere like zone 1, zone 6, you end up down here at about kind of 600 megawatts as your expected loss for any kind of given blackout. But if you look at zone 5 and you put all your renewables in there, okay, well, that's up at the kind of 1100. It's almost double the risk, depending on where you put the renewables. So now we also were like, okay, now we need to start trying to get into the details here, because it's like it's too many things to look at, too complex. So let's just look at these two, okay, just zone 6 and zone 1. Okay, these are two different zones. They have quite different properties. So zone 1 looks like this, zone 6 looks like this. And we were thinking back and we were like, okay, well, we saw loads and loads of under frequency load shedding. Okay, under frequency load shedding was the biggest cause of all of our kind of trips in the system. And that's going to depend on inertia. So let's create a case where we adjust the inertia of zone 1. So we're going to artificially lower it to exactly the same value as we have for zone 6. So we've made this kind of new comparison case where we've adjusted it. And because we were like, okay, well, there's all that under frequency load shedding. So my expectation is that this is going to have an effect and this is going to change my result. So then we run it and this is what the results were before. And when we reduce the inertia, it doesn't really change the results at all. So we basically get the same kind of result. So the impact isn't that dependent on the inertia. Like, so this is about as far as we've got. I don't have a nice summary that kind of explains what it is all caused by. We're still investigating it. But like the point is, like, you get some clues, you think that it's under frequency related and therefore it's an inertia problem. So you adjust the inertia to try and see the impact that has. And then you do that. And then you still find out that it's all affected by loads of other things as well. So there's some like outstanding questions that we have are things like, okay, is this actually a renewable problem? Or is this just a putting the generation all in one place problem. Maybe it's a centralization of generation issue rather than it's a renewable problem. And that's something that we need to answer.
I
So
have
yeah.
a quick question here.
Yeah.
Yeah. So for that, have you done this research that you did? Can you just go back to slide 85? Because you dropped the inertia of zone 1, right?
Yeah.
Have you done the other way around to increase the zone 6 inertia to the same as zone 1 and see if it changed?
No, we haven't yet. No, we have a whole list. It's a really good idea. We have that on the list of things to do. We have the kind of replacing with not with wind turbines. So yeah, replacing with synchronous generators, but locating those into the same place. We've got, unfortunately, as well, all these other axes that we need to investigate as well. So we're kind of working our way through it. It's not something that I would say we have bottomed out at this stage. It's very much this is a snapshot of where we're up to, where I think there's a lot of interesting challenges, and it shows that there's a lot of complexity in the problem and lots of things to look at. But it's not something that we've got to the bottom of yet.
The reason I'm asking that is because you have the renewable penetration increasing, right? So when it's increasing, then how your inertia has, your inertia will reduce, or your inertia will drop accordingly.
So we're displacing synchronous generators. So our loading in the system is staying the same. So when we add additional renewables,
you took one out, right? You took a synchronous generator out.
Yeah, kind of. So when we add more renewables, we'll run the security constrained OPF. It will dispatch wind first, provided it's secure to do so, and it will dispatch the wind before the more expensive fossil fuels. And then any fossil fuel plant that is essentially non-dispatched, we will disconnect from the system. So the addition of the renewables is decreasing the number of synchronous generators in the system, and so is reducing the inertia that way.
So if that's the case, then if you decrease that inertia down, it won't influence your high inertia situation because you're displacing that anyway. I suppose that this inertia is before you do the renewable penetration study,
yes.
Right?
Yes, exactly. Yeah. So this is the base case before all the wind turbines are added. Yeah.
Yeah, so my point is, if you are doing this high renewable penetration, then your inertia will be reduced to that amount anyway, because your synchronous generator will not be dispatched. So eventually, you're ending up as a 60, say 50% of penetration. Your inertia was low whatsoever, so you won't see the difference. But this is offline. You can talk about it later on. I just want to know your setup, so I don't want to drag this too long. Sorry about that.
No. It's an interesting point. No, we do. I know what you're saying. I think once we're down at sorry, I'm pointing at the screen that you can't see. When we're down at the low end of the stuff, we've still got some of that synchronous generation being dispatched though. So I get what you're saying, that at the higher levels, but I'm not sure we're high enough in terms of the dispatch to have essentially dispatched out that generation.
Yep.
Cool. Anyway, yeah, I'll get to the summary. Yeah, I guess the main thing, I'm going to argue that dynamics in cascading failures is an important thing to include. Particularly, I'd say that the non-global frequency behavior that we see. So there's some really interesting methods that exist about kind of extending AC power flow methods to have kind of frequency represented as a state, kind of within like an augmented power flow solution, including frequency states. The challenge is that I'm not sure how you do that and maintain a regional representation of frequency, and I think you do need to have some regional representation of frequency because that's causing these differences that we see. And I would argue, yeah, increasingly important as res increases, but I think as the presentation has shown, plenty of unanswered questions that we still need to focus on quite a lot. If you're interested in any of this, you should search for these names. Yitian is my RA. who's done most of this work. So if you search for her name, you'll find the papers on this. And while I'm here, I'll advertise it, but it's the reason I'm advertising this. So I run a kind of risk and resilience day every year in the UK. The reason I'm saying it is if you go to the website, not that you should come, you're welcome to come to Birmingham if you'd like to next March. But a lot of the past presentations and slides and information is put on the website as well. And so some of that stuff might be of interest if you're working in the kind of risk resilience space. So yeah, so that's it from me. Thank you very much.
Thank you, Robin. Now we have the Q&A part. Professor Lu Lin from NCSU asked you some excellent questions. So I would like to follow up on that. So any online audience, we will give the priority to you because we have plenty of time in the room, maybe 25 minutes. But any of you, if you have any question, feel free to unmute yourself and raise your question. Oh, so Jonathan had a question. What is the duration of cascade in your simulation and what's the effect?
Yeah, so it depends, I guess is the short answer. We're talking kind of up to a few minutes worth of simulation. So maybe up to about 5 to 10 minutes for some of the longer ones, which might be a slightly aggressively quick thermal tripping of lines. But otherwise, the problem we have is that we're sat there essentially waiting for a long time with a line to be overloaded. The system is otherwise stable. And so we don't want to run, let's say, 10 minutes of essentially no dynamics of a stable system, only for that line to then trip and then to move on to the next stage. So we slightly accelerate some of the thermal tripping aspects so that we can get everything into about 5 or 10 minutes.
Jonathan, does that sound good to you?
And what's the effect, if any, of secondary response? So I do think we do have the secondary response modeled in this. I think it has a small effect. It's not the biggest effect, to be honest, because most of the time the frequency is the biggest battle to maintain in the system, and so most of the frequency containment is being done by the primary and the very fast response. We have some periods where you might then see a little bit of secondary response, just kind of slightly bring up your frequency back to closer to kind of, well, for us, I guess it's 60 hertz, right? It's a US system. So closer to 60 hertz before the next trip and the next problem starts to happen. So it has a small effect. We haven't looked, and we could look at what happens if you just disconnect it, if you turn that off, and what effect that has. It's another one on the list, right? I guess that's the problem. We've got a long list of things that we want to study and look at and work out what do we need to include. And I think we're just kind of starting that process of looking at each of these elements in turn and saying, if we change this, what impact does it have? If we change this, what impact?
Okay, sounds good. Jonathan, if you have more questions, feel free to speak out. At the same time, for the online, oh, Jonathan, you are muted.
Yeah, okay. I mean, I guess you're more interested in the instantaneous effect, so you limit the duration, but I think, I mean, that limits your ability to study the long-term effects. So
yeah, no, definitely, yeah. I think, to be honest, if we wanted to go to long term, I think the best way to do that computationally you'd probably have to do some co-simulation where you model the dynamic state for a short-term transient period, let that settle. Once that settles, flip into something essentially kind of more quasi-steady state,
right,
and then run that until another event occurs, and then swap back, simulate that event. And I think you'd have to probably switch between the two.
Mhm.
Otherwise, I think you're spending too much time essentially not simulating useful stuff and essentially wasting computational resource. So I think there's a space to do that. It's another one of the fun things to look at.
Okay, thanks.
Thank you, Jonathan. For the online audience, I mean, if they are students, feel free to even ask basic questions. I think Robin is happy to introduce you to the research. Any more questions from online?
Actually, I have one more question regarding the simulation setup. So when you do the N-1 or N-2 contingency analysis, the initial schedule of the system is very important, right? Because you cannot turn on generator online once there's a generator outage or transmission line outage happens. So how would you actually decide who's online and who's not online? Is it because you have an economic dispatch going and then save some reserve there to cover
Yes.
the largest contingency?
Yeah. So we have it's a security constrained OPF, so it's economically dispatched, and that does make a difference. We've done some other studies as well where if we look at particularly when you look at lower loading levels, because if you're using an economic dispatch, you tend to dispatch a lot more. Obviously, if you're cheapest generation, that might lead to a lot more kind of centralized resource if you have a large centralized resource of cheap generation, which can actually lead to kind of higher localized loading of certain lines at lower system loading, because you essentially have the generators running at 100% or whatever, fully dispatched, but you don't have the local load consuming it. So instead, the lines radiating out from that generator are really highly loaded. And so you can find increased risk at low load in the system, which feels a little counterintuitive. So we run that economic dispatch, and then exactly what you said. We essentially have a kind of a reserve margin that we run to. I think it's about 20%. And then on top of that, we then, if we need, will add in extra frequency containment for fast response, because sometimes the reserve margin alone isn't enough to it might catch your nadir, but it doesn't it might catch your like steady state frequency drop, but it's not enough to catch the nadir in a light low frequency system, because you get like a kind of inertial bounce where it drops quite low to start before it recovers. So we need to add fast frequency response to contain that as well. So we have all of those things, I think, represented.
Yeah, but my last question would be, if you do that, your FFT, the faster frequency FFR, faster frequency response, that one actually is the one that you are arresting the frequency initially. And then that also determines how much load you're going to lose along the way. So what is your ratio between FFR and then the traditional generator reserve?
So I can't remember. So we don't set it as a ratio. We run the dispatch. We have our reserve. We stick essentially primary control on every synchronous generator with a standard droop of about 4%. If that contains the frequency for the largest in-feed loss, so if that contains the nadir to our limit, then we don't add any FFR. If it's not going to contain the nadir, we'll then start adding the fast frequency response until it's contained. So we do it with that process.
Okay, thank you.
So we treat it like it would be an additional service that you would procure on the kind of on a when you need it basis. So based on the dispatch.
Yeah, it would be actually good if you have that kind of FFR also mentioned in your different cases when you have different penetrations, how many was triggered because the FFR triggered. And then that probably will be helpful to see your different inertia cases, how this whole thing works.
Yeah, no, that sounds good. Yeah, it's a good idea.
All right, thank you, Professor Lu. Now we will switch to the in-room Q&A, and for the online audience, feel free to shoot your question into the chat box or interrupt us. Yeah, thank you. Any question to the speaker, any level, please?
Yeah, my question would be, is regarding the N-2 contingencies. I was wondering why you considered only the dotted lines. You didn't consider like modeling faults, for example, for tripping lines or tripping of generator, something.
Just to make the problem smaller, I guess. So we're looking at, yeah, any two line outages at once. So we're not trying to model it necessarily what the fault is that causes it. We're just looking at, in this work at if any two outages took place at any time, any two line outages, what would that be?
Because I thought like most of these cascaded issues is caused by an overloaded line that is tripped. Is it that case? Or?
Not necessarily. It depends. So it depends what it might be caused by, like a storm or something, right? So you might have a storm, you might have a planned outage on one line and then an unexpected fault on another line in another part of the system that then causes you to have essentially an N-2. You can have all sorts of different potential initial things. So there's some other work on the kind of the modeling the fragility of the system, and like say passing a storm event over a network and looking at what's the probability of certain lines being affected, of being damaged, of failing as part of that, and then modeling that through into kind of subsequent cascades as well. But then that's doing a lot more work on the front end initial shock event modeling side of things. For this was much more like assuming something has happened, how does that then propagate through the system? So you could do it for generator outages and stuff like that as well, but those will typically be far more significant as well.
Yeah. Is it like faster if you just model a line outage instead of the thermal or waiting until it exceeds a thermal?
So for the initial outage, we are just modeling the initial outage. So to kickstart it, we're just disconnecting two lines.
Okay.
And then once we then get into the rest of it, it's for those lines that then become overloaded as a consequence of that. Those are then tripped after a period of time due to the thermal tripping.
I see. Interesting. Thank you.
A very basic question that they mentioned at the start of the presentation. Say there is a varying frequencies in England.
Yes.
Yeah, and for your testing case, you are doing the simulation of Texas and Illinois, right?
Yeah.
Do you still consider that kind of varying frequency in regions, or?
Yeah, so you're still seeing that varying frequency. So what we've got to be a little bit careful of, I guess, is that the Illinois case is modeling a region of a network which is not actually a standalone network. So that's another thing that we need to be a little bit careful of, is that ultimately that network is interconnected with other networks, and its frequency variation is going to depend on what it's connected to and how much that is essentially holding it up, which we're not modeling. The Texas case, I guess, is a little bit maybe more realistic because Texas is its own standalone network, right? So if you're modeling Texas, you're then modeling essentially a complete synchronous network. And so the frequency variations that you see within that system are probably going to be more representative of the actual frequency variations you'd see in the system. But yeah, you can, if you plot frequency over time, you see it ripple through the system kind of thing. So you'll see a disturbance happen, a trip in a certain location, and then the frequencies will kind of like, the effect will ripple across the network depending on the inertia distribution, the impedance, the connectivity of the system.
Yeah, it sounds like the tolerance of different parts is kind of different.
Yeah. I mean, and so obviously if you have a disturbance in a low inertia part of the system, you should see that frequency drop much faster. And then you're likely to see that have more of an impact on the system.
Excellent.
I have a very tiny question. So in the zone comparisons that you did, so zone 1 and zone 6 had really low expected value.
Yeah.
But the only common indicator that I could see between those two zones was like the degree of connectivity was high, like on average for both the zones. I can't intuitively understand the relation between like the degree of connectivity and let's say frequency. like the frequency?
No, neither can I. And it might not be it's a frequency dependent thing that's causing it. It might be that it's a line loading issue that's determining the kind of difference in risk between those areas. I think, to be honest, it's very, very early, and we don't have a kind of definitive conclusion on precisely what's causing those differences there. But yeah, we need to just need to investigate it more. The problem is it's very hard to, well, with when you take an actual network or something representative of an actual network, it's very hard to kind of control precisely for certain values. Like you can't easily change line node degree, right? You can't, but because if you add additional lines, you're then also going to affect the power flow, you're going to affect the line loading at the same time. So it's very difficult for you to control for just one of those various variations. And we don't know that those are even the right things to look at. Those are just ways that we have summarized what those zones look like. But it's a varying thing.